Hi everyone. You probably know the law of sines as the following. Given a triangle ABC, where lowercase a represents the length of the side opposite angle A, lowercase b is opposite angle B, and lowercase c is opposite angle C. In this triangle, a over the sine of A equals b over the sine of B, which equals c over the sine of C. But not everybody realizes there is another quantity to the law of sines. Turns out all three of those ratios are equal to 2 times r, where r is the radius of the circle circumscribing the triangle. So we're going to prove this extended version of the law of sines. So to do it, we'll divide it into 3 cases. Case 1, we'll consider a triangle like this, where the center of the circumscribing circle is inside the triangle. This will happen whenever the triangle is an acute triangle. Let's say that's angle A, B, and C right there. Okay, to help me prove this, I'm going to draw a diameter through vertex C, like that, and we'll call this point on the circle P, and I'm going to draw the line segment PB. Okay, I want to make some observations about this diagram so far. Arc PAB, or rather arc PAC, is 180 degrees because we have a diameter through P and C. It's half a circle. Angle PBC is an inscribed angle that intercepts that 180 degree arc. So from our previous video, we know the measure of angle PBC is half of 180 degrees. In other words, that's a right angle. So we have a right triangle, PBC. In this right triangle, we can mention what the sine of P is equal to. Okay, it's equal to this opposite side BC over this hypotenuse PC. But BC will be called lowercase a because it's opposite angle A in triangle ABC. And PC is a diameter here, which we're going to call 2 times capital R, the radius of the circumscribing circle. One more observation we'll make about this picture. Take a look at angle A. It intercepts arc BC here at the bottom. It's an inscribed angle that intercepts arc BC. So it measures half of that arc. But look at angle P here. It intercepts the same arc. It's another inscribed angle with half the measure of arc BC. So that means those two angles are congruent. And so I can replace the sine of P with the sine of A. But I can take this equation and rearrange, and I find out that A divided by the sine of A is 2 times R. Now there's nothing special about angle A in this picture. I can do the same proof from the point of view of B and from the point of view of C, and I'll find that the ratio B over sine of B is also 2R, and C over sine of C is also 2R. So that establishes this extended law of sines in this case. Let's look at another case. In case 2, we'll look at a triangle where the center of the circle that circumscribes it is outside of the triangle. This would happen whenever the triangle is obtuse. Let's call this point here A, this point B, and this point C. And just as before, I'm going to draw a diameter through vertex C, like that. Okay, and I'm going to call this point P, and I'm going to join it to B. Okay, so again, since I have a diameter here, I have a right angle right here. Angle CBP is an inscribed angle that intercepts this lower arc PC, which is a 180-degree arc. So that makes that a 90-degree angle, half the measure of the arc. So in that right triangle, I can write down what the sine of P is equal to. It's opposite over the hypotenuse. Now the opposite is side BC, and the hypotenuse is PC. But again, BC is typically called lowercase a, and PC being a diameter is 2 times r. Now I want to compare angle P with angle A. Angle A intercepts this large arc BPC, and angle P intercepts the remainder of the circle, arc BAC. Together, this angle and this angle intercept two arcs that total 360 degrees. Okay. That means those two angles we just marked total 180 degrees, half of the measures of the arcs that they intercept. So angle A plus angle P is 180 degrees, which makes angle A 180 degrees minus P. Okay, so that means the sine of angle A is the sine of 180 degrees minus P. You can use a symmetry argument to find out that that sine of 180 degrees minus P is equal to the sine of P. Or you can use a trigonometric identity that says this is equal to the sine of 180 degrees times the cosine of P minus the cosine of 180 degrees times the sine of P. Now the sine of 180 degrees is 0, so that term cancels, and the cosine of 180 degrees is negative 1. So this simplifies to the sine of P. So the sine of A is the sine of P. So going back here, we see the sine of A is equal to A over 2r, or rearranging again, A over the sine of A is 2r, just like in the last case. And there's nothing special about angle A. You can make a similar argument for angles B and C. So that establishes the extended law of sines in that case. So finally, the remaining case is what happens if one of the sides of the triangle passes through the center, like this. So let's say that's A, that's B, and that's C. This is actually the easiest case. Angle A opens up to this lower arc BC, which is a 180 degree arc. So angle A is half of that, it's 90 degrees. So this is a right triangle. So the center of the circumscribing circle lies on one of the sides in the case of a right triangle. Okay, so we can establish the law of sines using simple right triangle trigonometry. For example, the sine of A would be 1 because the sine of 90 degrees is 1. And we've got A over the sine of A, therefore, is A over 1, which is A. But A is this side opposite angle A, which is twice the radius of the circle. So A over sine of A is 2r. What about B over sine of B? Well, let's write down sine of B. The sine of angle B is this side, lowercase b, over the hypotenuse, which again is 2r. So rearranging, we get B over the sine of B is 2r. And finally, the sine of C works the same way as the sine of B. The sine of C is the side opposite, which we call little c, over the hypotenuse, which is 2r. So rearranging, we get the desired result. So we've established the law of sines in case 3 as well. So whenever you think the law of sines in the future, think of this extended version. It can be useful, and we'll make use of it in problems in future videos. Thanks for watching.